there.
Okay, let's see. Just if I can get a peek at that. Okay,
So
we're already starting.
Next speaker, Arthur Adams, mapping exoplanets and brown dwarfs across time and space.
Well, thank you all so much. I know I'm supposed to sit here or stand here. This is my first time at this conference. It's a great privilege to be able to talk with you today. I have a bit of a scatterbrained talk today, because I work on multiple things, and so I have maybe on average about 4 minutes to give you just a taste of the things that I'm working on today. But I'm already really excited about all the results I've heard so far. In a short period of time, I need to convince you that we can do some mapping across time and space. So I'm going to talk a little bit about variability monitoring of at least one target. A paper that's in press for 2MASS 1207b will be the first part of my talk. So I'm going to give you a little bit of a Spumoni talk. That's a little bit of a taste of things, the ice cream, the pistachio, the cherry, the chocolate. It'll help you remember because I'm going to be going so quickly. So 2MASS 1207 system, if you're unfamiliar with it, it's one of the first directly imaged systems of the Planetary Mass Companion. It's the pistachio because it's a young system, so it's rather green, so it helps you remember that. I'll start there. I think there's going to be probably some more talks about variability. The picture I always come back to is that of Jupiter. Jupiter, even though it's at a different temperature range as 2MASS 1207b, it's your mental image of how Jupiter's variability will set a nice image for what we believe is going on with 2MASS 1207b, in that a paper by G in 2019 looked at Jupiter as kind of like an exoplanet, if you want. And the things to keep in mind is that Jupiter is variable around, in the mid-thermal infrared at about 1% across the rotation, and the modulations come from these changes to the size of the equatorial bands and, of course, the rotation from the Great Red Spot, right? So these are sort of like the pictures of things you should be thinking about. Here's a false color image of 2MASS 1207, right? So if you're familiar with VHS 1256b, which is kind of the bigger cousin, right? It's like a sized down version of that, but the temperatures are remarkably similar. And so for the folks who are very interested in these LT transition objects, where you expect the silicates to sit right in that sweet spot near the photosphere, and maybe that clouds and temperature changes are driving the variability, you might be interested in an object such as the planetary mass 2MASS 1207b. So I was fortunate enough to be hired to work on and analyze the first analysis of this data set from Yifan Zhou, who's this professor at University of Virginia, and had this lovely program that I was able to work on to see these near-spec prism observations across a rotation period of this companion. So I don't have a lot of time to go in this week. I'm happy to ask questions. But it appears to be, long story short, that the picture is at least consistent with these sorts of variations in these cloud fractions, perhaps due to these changes in these band fractions that I pointed out with Jupiter, right? We don't have an actual image of this, but at least the picture's consistent. If you look at a paper such as that authored by Zijie Zhang that came out early last year, who used HST, photometric variability, to argue that this cloud modulation is the most consistent picture, of course in silicates, unlike Jupiter. Our results seem to at least be consistent with that, but unfortunately we did not see a clear periodic signal as we would have expected for monitoring this companion through what we believe to be one rotation period. So unfortunately I don't have a better picture for you of what's going on with this object. It just seems like it's right at the limit of what we're sensitive to with this sort of observing mode with JWST. Prism mode, the variability is right about that 1% on average, maybe 2%. That we explain more in the publication. It's out in press currently. But one thing I think is interesting is if you look at the host, right? So this is a 2 substellar object system. So one thing that's very interesting is you have something like a 2500 Kelvin host that has a rich structure in the variability, and so they were observed simultaneously, right? So one thing that, this data set, we only did a very cursory analysis, right? This would really be something that you'd need something of the sophistication, maybe approaching Jerry or Alex's sort of approach to really get at this in. But, from the variability map, right, I'm showing here in this color map, you appear to see this wavelength-dependent phase variation on the largest scales in wavelength. And then if you zoom in farther, I am glossing over many details, but there was some interesting kind of variability features, and one thing that stood out to me and I couldn't explain was that unlike the companion, which should have methane but does not show it, the host while not showing methane necessarily directly or something like that, it appeared to have variability at the wavelength that you would imagine you'd be sensitive to. Now, extreme caution with this interpretation. We put it out there, said this is an interesting feature, but I will say I was very skeptical, but another paper by some authors who analyzed the high spectral resolution non-time series set for the host also have difficulty resolving this feature without including some sort of hydrocarbon. It's very tenuous. Again, this will require more thorough analysis. Okay, so I just gave you a sneak peek of a young system. Now we're going to the cherry part of the talk. I'm excited about this other system, HD106906b, a very different system. The reason it's the cherry flavor is because it's unusually red. For its spectral type, and that's among other things that are peculiar about the system. If you know the system, you know it's quite a rare and interesting system. Okay, so unlike the IFU imaged 2-mass-1207 system, this one is a very widely separated system, right? So a binary F-dwarf in the middle there, and then you have this very wide orbit companion right maybe about the deuterium burning limit, and its projected separation is something like 700 AU. Here you're sitting, unlike the 2-mass-1207b, it's a little bit warmer, so it's sitting at the early L type. So a comparable thing, same way with VHS 1256b for the other system, a comparable spectral type would be something like beta pig B or 2-mass-2208. These are things that are sitting right here up in the L dwarfs. And what I want to remark on in the peculiarity of the system is that it does have HST variability monitoring as was originally done for 2-mass-1207. And what's interesting about that, so the work of Yifan and also Marta Bryan, I know Jerry's also done similar stuff with these rotation constraints, is that we have an estimate of the rotation period because we have a V sin I estimate. And so you combine the radial velocity with this photometric monitoring. What seems to be happening is that if you resolve these, the implication is that the viewing inclination is very close to pole on, right? So it's this 14 degrees where 0 would be directly looking along the pole axis of the planet, or the companion. And this is interesting in its own right. So this is kind of a peculiar viewing geometry for the sorts of companions. And also from works such as Genaro Suarez's papers and others suggests that if you should be seeing redder objects if you're looking more equatorial view because of the way that the cloud opacity changes, or we expect it to change as a function of latitude, or at least that's the interpretation that's done from these empirical analyses. And so this is there's these strange tensions. This thing is, we are currently interpreting it as being this pole-on view, but it's quite red even for the comparable spectral types. Another thing I don't have a lot of time to go into detail is that there's actually unresolved issues with the photometry. We actually don't know how red this object is. So there's a lot of things that need to be unraveled. And so I'm very interested in characterizing this object. And it would be really cool to see if this is truly a peculiar system or peculiar object, or is this something that we're kind of misinterpreting. I'm going to spend the last 3.5 minutes. I apologize again. We're doing a very quick whirlwind tour. We're going to move to the chocolate part of the talk, which is, of course, brown dwarfs. And I am interested in a bunch of different things, and one thing I've done in the past is this eclipse mapping. And so this is the spatial part of the talk, right? Of course, there's time aspect, but so we just talked about time variability. And so one thing I've been very interested in and had the opportunity to work with is an upcoming data set of these sample of white dwarf brown dwarf systems that folks like Yifan Zhou and co have got these data sets for. Graduate student Daphne Borowski-Lang is working with collaborators to analyze some of these spectra in longitude. So there's great stuff coming out. I encourage you to follow up on that when they come out. For my purposes, I'm interested in whether we can take the subset of these samples where, as you're seeing here, the brown dwarf is eclipsed by its white dwarf host along our viewing geometry. Can we apply the eclipse mapping principles that are done often for hot Jupiters now in close-in systems for these sorts of systems? In terms of exoplanets, these are kind of treated as, for my purposes, as an analog, a high internal heat flux analog of hot Jupiters. So we're moving up in this plane by Showman et al. To these high external irradiations Of course, you have a different SED for your host, but that's a different story. But if you're familiar with some of the recent results of Ryan Challoner, Megan Mansfield, and many other folks are out there, I'm glossing over many names. There have been these detections, evidence for detection of latitudinal asymmetry in the brightnesses of this, which then you compare with models of circulation for these close-in planets. I realize this is a direct imaging crowd and a high contrast thing, but I thought this was interesting because there's this analog with these hot, brown dwarf objects, and I think it's also interesting kind of to draw this comparison right in this space where you have these high internal heats. So bottom line of this in my last minute and a half, are we sensitive to, say, a latitudinal asymmetry or some other structure in this interesting geometry of occultation? Just as a refresher, because I don't know how I'm familiar with, phase curves alone can probe the longitudinal structure of these objects as they go through a rotation. And it's been known that you can try to probe the latitudinal information through if you have a secondary eclipse, right? And so I'm showing some work. I believe Shen-Yu Tan also, it was kind of running a lot of these circulation models and getting this prediction, these in this case for HST light curves that are showing you that there is a structure predicted by the GCMs, but the signal to noise was not high enough to get this. So the question is, and this is ongoing work, so I don't have a definitive answer for you today, whether we can do this as well. So I'm writing code, we like to release open source packages. Every code needs a name, so I came up with Luna, I can explain it. But it's me trying to take these principles from my own work and from colleagues that are doing this great work in eclipse mapping and try to apply this in this unique regime to see, can you learn something about the brightness structure of these from this eclipse pattern, right? So it's a trickier problem than I anticipated. In the initial tests, that I see I have 2 seconds left, it's promising. Just trying to show, how you interpret the information you get from the occultation. It's promising, but there's more work. I hope to have more information for you on all these fronts in the future. But again, it was a great privilege to talk with you today, and I'm happy to answer questions.
Hi, great talk. I had a question about HD 106906b.
Sure.
Is there a potential for some sort of circumplanetary disk or dust that might be making it more red than expected?
Yeah, that's an excellent question. So my understanding is no, and well, I guess I can't rule it out completely. The age of the system is about 15 million years. There's a known debris disk in the system. I'm not sure whether I could definitively say, no, there's no circumplanetary disk around the companion. I just don't know if there's been a detection of that. But I will say for the 2-mass total 7 system, there has definitely been detection of the circumstellar disk around the brown dwarf host, and there is, I believe, a tentative detection of some material around the planetary mass object too. So that's very interesting. It's also quite young, but 106, not sure.
In the HST data for 10696, I thought I saw it might be extended, and so we should look into that question a little in greater depth. There are some hints.
Okay.
Yeah.
Yep.
All right. Oh.
Sorry. Yeah, I don't think anyone can really answer that, but what's your take? Like, how do you think those planets get where they are at?
Can you repeat your question? I'm sorry.
How do you think those planets get to where they are at? So like 106, it's pretty far away. It's at 650 AU, I think, right?
Yeah. Yeah. The question is, how did 10696 come to be? And it's an unresolved question, as you pointed out. There's been papers out in the literature. I think Moore is the name of one of the papers. There's been several. I'm missing some that look at the idea that it could have been formed within the disk that is now the debris disk and then scattered out so that you just need enough, if it's going to form, via something like a planetary sort of formation pathway, you need enough material, and you need it to be formed in a place enough material and then scattered out. The atmospheric analysis I did a couple years ago seemed to indicate the C to O ratio, which I know is kind of not the full picture, is consistent with the hosts, so there wasn't any indication that it formed like that. So it's possible it forms like a binary. I've talked to folks who think maybe you have enough material to form it out near in situ. It's kind of hard to say, but I still am partial, I guess, to the scattering hypothesis.